How do you prevent controller windup when tuning PID? Imagine trying to steer a boat in rough waters. If your steering gets stuck or overcorrects, it can cause the boat to spin out of control. That's similar to what happens with controller windup in industrial systems. When the control system's integral part keeps accumulating error during saturation, it can lead to overshoot and instability once the system responds again. Preventing this is key for smooth, reliable operation in robotics, manufacturing, and process control. One common method is using anti-windup schemes. These modify how the integral part behaves when the actuator hits its limits. For example, integral clamping stops the integral from increasing once the output reaches a maximum or minimum. It's like putting a cap on how much error can build up. Another approach is back calculation, where the controller adjusts the integral based on the difference between the actual actuator output and what the controller wants to send. This keeps the integral from growing too large when the system is saturated. Setting explicit limits on the integral term is also effective. You can define a maximum and minimum value for the integral. When the error causes the integral to go beyond these bounds, it stops accumulating. This way, the integral stays within a manageable range, preventing overshoot and oscillations. Tuning the proportional and derivative gains before adding the integral gain helps too. If the system responds well without the integral, then adding it gradually reduces the chance of windup. Using feedforward control is another smart move. It predicts how the system should behave based on known disturbances or forces, like gravity or load changes. This reduces the load on the integral part, making windup less likely. Including an actuator model or signal limiter inside the controller helps it recognize when the output is saturated. When it detects saturation, it adjusts the integral to avoid error buildup that can't be corrected immediately. Monitoring the system during operation is also important. If you see signs of windup, such as large overshoot or oscillations, you can tweak the integral gain or activate anti-windup features on the fly. This is especially useful in smart factories and advanced manufacturing where conditions change often. In short, preventing controller windup involves a combination of strategies like anti-windup schemes, setting limits, tuning gains carefully, and using predictive controls. These methods keep your control system stable, responsive, and ready to handle the demands of modern robotics and process instrumentation. Properly managing windup ensures your automation runs smoothly, with less overshoot and more precise control in every step of manufacturing or robotic operation.